Sir, 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 you're saying something? We are not getting your voice.
Oh, yes. Sorry. Forgot to unmute myself. Okay, so today we are going to start uh, sublattices, and this is the last topic of unit number 2, that is lattice. And we will discuss sublattice, distributive lattice, as well as complemented lattice today. Okay, so before starting these things, what is the definition of sublattice? So first of all, we need any lattice like L star plus circle. Last day, if you recall the star, like last day I told you L star plus circle. If I have this structure defined, this structure implies this is a lattice as an algebraic system. As an algebraic system. All right. Similarly, if something like given like A D, A is a set and D is not D exactly, A R you may say. A is a set, R is a relation. That is also maybe a lattice, but that is called a lattice as a poset. So there is two type of lattice. One is lattice as a poset, another one is lattice as an algebraic system. We have already discussed, and we have already discussed how to prove that this is a lattice as a poset, and how to prove that this is lattice as an algebraic system. There's two specific method to prove those stuff. Okay. Now we are going to discuss sublattice. Sublattice means we must have a subset. S is a subset of L. Okay, so L is the L star plus circle is going to be the lattice, and S is a subset of L. Okay, any subset. Then what we can say, A star plus circle. What we can say, A star plus circle. This one is called a sublattice. It's called a sublattice of L star plus circle. Okay, we can say that A star plus circle is a sublattice of L star plus circle if GLB and LUB elements of each of pair of elements of S. Okay, LUB and GLB of all pair of elements of S must belongs to S only. That means that particular subset. So pick the elements from subsets. Okay, pairwise, any pair of elements. Calculate GLB and LUB. All the GLBs and LUBs belonging to S only, that subset only, not outside of the subset. Okay, if I can find like this stuff, then what I can say that A star plus circle is a sublattice. This is the first foremost condition. Okay, now what is the meaning of what can be implied by this GLB and LUB? GLB means A star plus A star B, and LUB means A plus circle B. Both should be belongs to S only. Let's talk about some example. Check whether the following subset are sublattice of a lattice S24 GCT LCM. So S24 GCT LCM, this is a lattice. Okay, we can prove this as a lattice. This is a lattice as an algebraic system. Now what you have to show, you have to check the following subset. This is a subset A of S24 because S24 is 1, 2, 3, 4, 6, 8, 12 for 24. So this is your S24. So take any subset from S24. Okay, like 1, 2, 3, 6 is any subset of S24 is A. Now you have to check that whether A is a sublattice or not. Okay, under the GCD and LCM. So what we have to do, we have to create two matrix. One is GCD matrix, another one is LCM matrix. To prove this is sublattice, we have to draw the tables of LUB and GLB. So first GLB table. GLB table means GCD table, because we know that GCD equals to GLB here, right? How many elements are there in the subset? 4 elements, 1 2 3 6. So calculate, like write 1 2 3 6 over here. I think you know how to calculate GCD. So take each pair of elements and calculate their GCD. Like if I talk about what is the GCD of 3 and 6, GCD of 3 and 6 is 3. GCD of 6 and 2, GCD of 6 and 2 is 2. Just put there in that GCD inside in the intersection of those elements, and we find the matrix, GCD matrix. Each and every elements inside the matrix. Look at this: 1 1 1 1 1 2 1 2 1 1 3 3 1 2 3 6. Every element is belonging to A only, not from outside of A. All elements either 1 2 3 6. Okay, that means it's satisfying. That is the things we have to check. If I suppose, if I find after calculation of GCD, if I find some element is 5, but 5 is does not belonging to A, so it's not a sublattice. We'll stop there. We can say that it's not a sublattice. But here each and every element is belonging to A only, that subset. That's why we can proceed for sublattice. But this is not only the one condition, also we have to check LCM matrix. Also we have to check LCM matrix as well. Like LCM matrix tells us all 4 by 4 matrix, I mean all 16 elements. Look at this, each and every elements, all elements are belonging to again capital A. That means either 1 or 2 or 3 or 6. What that implies? This implies each and every elements from those tables are belonging to capital A. That means GCD matrix and LCM matrix satisfying is having all elements, and all those elements are belonging to 1 2 3 6. So 1 2 3 6, that A is a sublattice of S24. So finally our conclusion is A is a sublattice of S24. All right, hope it is clear to all of you. Please write C on chat box. If it is clear to all of you, please write C on chat box if it is clear. I think it's very easy content. It's clear to all of you. Write C on chat box. Quick C on chat box. Cool. All right. So similarly, let's move on to the next question. Sorry. So next question is B equals to 1 2 3 8. 1 2 3 8. Again, the same type of questions. You have to check whether this is a sublattice of S24 or not. S24 is the main subset, main set. Okay, so it's a sublattice of S24 or not under GCD LCM. You have to calculate GCD matrix, LCM matrix, okay, and check each and every element, each and every pair of elements, and calculate their GCD LCM. If you find all GCD and LCMs belonging to B, that is either 1 or 2 or 3 or 8, then we stop there. Okay, we can figure out that B is a sublattice. But if I find any elements, any GCD or LCM, any of them are not inside B, okay, outside of B, then we will stop there and we will write that this LCM of this is going to be not equals to not belonging to B. So we will, this B is not a sublattice of S24. So according to the point, write down your conclusion on chat box whether B is a sublattice or not. I want the answer from you. According to the point, I think you get it, how to check sublattice. Just write if it is sublattice or not. Not only just writing, you have to write the justification. If it is a sublattice, why? And it's not a sublattice, why not? Just mention that line on chat box, quick chat box. All right, excellent, good response from Matthews. So what we can write, 2 plus circle 3, that is LCM of 2 3, and that is equals to 6. So LCM of 2 3 is 6, and which 6 is 6 does not belonging to B. So we'll stop there. B is not a sublattice of S24. This is direct we can write. Okay. Similarly, move forward. Check whether the following subset are sublattice of n GCD LCM. Check it quick and write down your answer on chat box. Which one is a sublattice, which one is not, both, if both are not, why both are not. Just write down your answer on chat box. Okay, with justification, and just do it quick because I have to cover two more topics today. Okay, so try to be quick enough. Okay, I'll give you 3 minutes time to complete this stuff. Okay, same type of questions. N is the set here, not n means it's natural number. Okay, don't need to take care about n, because what you have to check, you have to check with this a. Let's say this is 1a, let's say this second number is b. Changing the name of the set, it's b. Second question is b and the first question is a. Go for it and write down your answer, which one is subset, which one is sublattice, and which one is not, or both are sublattice, both are not, like this. Write down answer on chat box. All right, Arafat response as all the elements of GCD is belonging to A, so is a sublattice of N. Hamnat response that 1 to 5 is sublattice of or sublattice because yes, okay. A is a sublattice. Everyone is responding A is a sublattice. I'm not responding that B also sublattice. Okay, good. For your information, just check it again and again. Okay, just try to calculate each and every LCM and GCD. All LCM and GCD should be belonging to A and B only. That is the main condition. Not belonging to N. David, not belonging to N. GCD and LCM should belongs to A and B only. That much you have to check. Not belonging to N. They are always belonging to N. That is not my concern. Our concern is that GCD and LCM should belongs to A or B or not. Okay, Matthews. Good response from Matthews. Good response from Matthews. All of you can refer Matthews' work. All right. So first one is a sublattice because all elements we take LCM of 1 2, LCM of 1 5 1 2 5 5 10 anything, GCD of 1 2 1 5 2 5, all belongs to A only. Okay. Now number 2, B. In B take 5 and 7. So LCM of 5 and 7 is 35. LCM of 5 and 7 is 35, which does not belonging to B. So we will stop there only. Okay, just you have to write that much. LCM of 35, 7 and 5 is 35, does not belonging to B, and hence B is not a sublattice of N GCD LCM. Okay, next question. Next question. Check whether the following subsets are sublattice of PA in union intersection union. So for your information, A is given to you ABC, and PA is equals to phi singleton A B C AB BC AC and A. All right, this is your PA. Now A's and T is given to you. Again, I'm giving you 2 and 3 minutes of time. Check A's and T, which one is sublattice, which one is not. Write down your answer in chat box quick. All right. So Arafat says that S is a sublattice. Anyone else? But no response till now. Try to be quick enough. All right. Good. Matthew said that S is a sublattice. S is a sublattice of PA. Yes, correct. S is a sublattice of PA. Union C is BC, which does not belonging to T. That's why T is not a sublattice. Good. So let's go for the next one. The next topic is distributive lattice. So as I told you, so distributive lattice. A star is equals to A star B plus circle A star C. Okay. Just a minute, hold on. All right, so these are the distributive properties we have to check. As I told you, the distributive should be a lattice. The very first consideration is the lattice, and it satisfies A star plus circle B plus circle C should be equals to A star B plus circle A star C. That means star is distributed circle. Similarly here plus circle is distributive over star, and we all know that star means plus circle means LUB. So there is specific notes you have to follow. That distributive properties always true under three standard relation. And you know what are the three standard relations? Tell me, what are the three standard relations? Three standard relations. The first one is, second one is D, and third one is less than equals to D and subset. The standard relations we are going to talk about. This is a poset standard relation of the poset, and in this case, this is a yes sir, yes sir, no problem, no problem, everything's okay. So R is actually subset here. Whenever I'm considering this nodes, the first one is
Sir, you explained.
distributive. Yes.
Your screen.
Hello.
Sir, you stop the presentation.
Okay. Just sorry for the interruption. I think some network issues there. Just wait. Let you know about the stuff. I think screen is visible. Please acknowledge me. Screen is visible or not.
Yes, sir, we can believe.
Okay. Thanks. So in the first case of distributive property, I told you the distributive property always holds true under three standard relation. The first one is less than equals to, second one is D, and third one is subset. So first case, whenever R is a subset, your distributive properties look like this one. That means this holds true. You may ask me, sir, how it holds true? You can check it by using a Venn diagram. Notes, because don't need to prove it in exam. Okay. And the second one is whenever R is equals to less than equals to. Suppose R is less than equals to, then this have minimum is going to be your GLB and maximum is going to be LUB. Then true. Sorry, uh, A plus circle B star C equals to A plus circle B star A plus circle C. The second property is the first one in this case. Okay. And similarly, whenever R equals to D, relation is the divides relation, then GCD is your GLP and LCM is your LUB. So then also distributive property holds true. So you have to mm, memorize this concept for long, that distributive property always holds true under any circumstances for the standard relation less than equals to D and uh,
Sir, your screen is gone
yes.
again.
What is going to happen? Sorry, just wait. Working on it. I'm fixing it up. Is it visible now? Is it visible now?
There it is.
Okay. All right. Okay. So sorry for the interruption. Next. So the thing is that distributive property always holds true under this standard relations. Okay, so we will use this concept to prove one lattice is a distributive lattice or not. So let's go for this one. The first question is that you have to prove that R minimum maximum is going to be a distributive lattice. So R minimum maximum, that means a real number, set of real number is going to be the set, minimum is going to be your GLB, maximum is going to be LUB. So R minimum maximum, first of all you have to prove this is a lattice. Okay, you can prove it using three conditions you have to show. That is, one is commutative law, commutative, second one is associative, third one is absorption. Okay, hope you know this stuff. You have to show these three laws and you can do it. You have to show first this is a lattice under algebraic system. Now second, the number fourth property is a distributive property. So distributive property is a standard property, because in this case the minimum maximum, I told you in the last slide that minimum maximum, whenever you have minimum maximum as a GLB and LUB, distributive property automatically holds true. So we have to just write the distributive property in this for as a formality, nothing else. Just you have to write, don't need to show, don't need to prove, just this always holds true. Okay, because if you want to prove it up, you have to make few cases like when a less than equals to b, when b less than equals to c. Don't need to prove. Okay, it can be proven, but don't need to prove in exam. Just you have to write the standard formula, like a plus circle b means what, a plus circle b star c means what. That meaning is important here. This meaning is maximum of a comma minimum of bc. And what is the meaning of this? It means that minimum of maximum of ab comma maximum of ac. You may ask me, sir, why this is? Because I get it from here, from RHS. This is your LHS and this is your RHS. So we know that RHS and LHS also holds true. So directly write down LHS and RHS and so they are equal. That much you have to do in exam. Okay, in distributive property, whenever you are using distributive property under D less than equals to or subset, always do this stuff. Okay, directly you can show LHS equals to RHS in any condition. Okay, that is you have to write in exam. Okay, don't forget to write it. So finally we can write R minimum maximum is going to be distributive lattices. Okay, similarly you can prove this one also, this two, n GCD LCM, n GCD LCM. So now your task is that do this one and write down the statement on chat box. I will give you 5 minutes of time. So what you have to do, like this one, this is your distributive property of minimum maximum. Similar stuff you have to do for n GCD LCM. So n GCD LCM, take three elements a b c from natural number, three elements a b c from natural number, and give the priority to GCD and LCM, and so that distributive property holds true. Just you have to write it, don't need to prove it. Just write what is the meaning of each and every distributive laws. Okay, write it on chat box and I want to check your answers. Okay, write it within 5 minutes, only the first one, and the next one is your homework. This one is your homework, you can do it at home. So now only do the
Sir,
first one. Yes, Arafat.
uh, like taking the numbers 1 to 3 after taking
Hmm.
the P of A,
No,
we are going to
don't take 1 2 3, just take arbitrary ABC. This always holds
oh,
true. Just what you have to write, a star b plus
what
circle
does
c,
that?
that much you have to prove. What is the meaning of this? Just have that much you have to write on chat box, nothing else. Put your response on chat box. Not a difficult task. Just try. You have to write the meaning. This is your LHS. You have to write this equals to in terms of GCD and LCM. Over here is equals to again in terms of GCD and LCM, and this is the output RHS. So RHS is A star B plus circle A star C. So just write the meaning only. What is the meaning of this right here? What is the meaning of this right here? That much you have to do in any context. Quick, write this stuff and send it on chat box. We have to move fast. Quick. All right, Matthews. Written there is what? Perfect, Matthews. That is what actually we wanted. You have to write in both case, right, Matthews? Right. Try to write in the both part, like star over plus circle and plus circle over star. Yes, second one is we have written right. Correct, Arafat? All right. So you can do this for the next question as well, I hope, because the next question is a homework. So you can do this for that one also. So both are distributive lattices. Moving forward to the next concept, that is known as bounded lattice. So what is a bounded lattice? Try to listen carefully. It's an important concept. Important concept. So lattice L star plus circle is called a bounded lattice if GLB of L, not GLB of any two number or GLB of any pair of numbers. GLB of L means GLB of set. We are talking about the GLB of the whole set, and LUB of the whole set exist in L. We can call this L star plus circle is a bounded lattice if GLB and LUB both belongs to capital L only. So GLB we can denote as 0 elements. We can denote the GLB of L as 0 element and LUB of L as I elements. Okay, so what's the main concept is 0 element and I elements is both belonging to the set L, then L is known as bounded lattice under plus circle and star. So there is some notation of bounded lattice. Try to memorize L star plus circle. Since 0 and I element both are belonging to set, so 0 and I elements we have to include inside the notation. So this is called the bounded lattice. Now I will let you know how to calculate 0 element and I elements. Okay. So the thing is that S24 GCD LCM is a lattice. We know that. We all know that S24 GCD LCM is a lattice. Now what is S24? S24 is 1, 2, 3, 4, 6, 8, 12, 24. So 1, 2, 3, 4, 6, 8, 12, 24 is the S24. 8 elements is there. Now for all x belongs to S24, for all x belongs to S24, 1 divides x. Okay, what I can say, 1 divides x and x divides 24. Is that line clear? Is this line clear? For all x belongs to S24, check things. 1 always divides x and x always divides 24. X means what? X can be anything. X can be anything inside S24. X may be 1, x may be 2, 3, 4, 6, 8, 12, 24, whatever. Okay, take any number, take 8 at a time. Let's take 8 as x. So 1 divides 8 and x 8 divides 24. Holds true. Let's take 12. 1 divides 12 and 12 divides 24. Holds true. So you can take any number inside from S24. Always 1 divides that number and that number divides 24. And hence, since this property is satisfying, so finally, what is your 0 element? Your 0 element is 1 in this case. So 1 divides 24, x means 0 element is 1. X divides 24 means I elements is 24. The maximal element is 24 and the minimal elements of the set is 1. That is 0 elements and I elements. Please write C if it is clear to all of you. Please write C if it is clear to all of you. Write quick C on chat box if it is clear to all of you. How to figure out what is a 0 element and I elements. How to figure out a 0 elements and I elements from any set. Is it clear to all of you or not? It should satisfy this condition. 1 divides any number. Any number divides 24. And hence 1 and 24 is a 0 element and I elements. It depends on the set. Okay. Not always 1 is a 0 elements. Not always 24 is the I elements. Okay. Depends on the set. Or it may be possible in some set 0 element does not present. It's not present. Okay. So in that case, this is not a that is not going to be bounded lattice. Okay. It may be possible sometimes 0 elements outside the set or I elements outside the set. Then we can say that that set is not bounded lattice. So in this case, both 1 and 24 belonging to S24. Finally, we can say S24 GCD LCM is a bounded lattice. So S24 GCD LCM is going to be the bounded lattice because 0 element and I element both belonging to inside S24 only. Yes, SN, not all SN actually. Let's take an example like is 34. Yeah, in case of SN, it's always holds true. in the context of Sn is always holds true. So in the context of Sn, 1 is always your 0 elements, and n is always your I elements, always holds true in the context of Sn. Okay, for an example, let's take S35. So S35 is having how many elements? 1 5 7 35, 1 5 7 35. So you can write easily 1 dx x d35, always holds true for any x. Let's take another example like S52. What is S52? 1 2 13 26 52. 1 2 13 26 52, right? So 1 divides x divides 52, always holds true. So 52 is the I elements and 1 is a 0 elements. So in that context of Sn is always holds true. Okay, and n is going to be I elements and 0 elements is a 1 whenever we have Sn as a set. Okay, so Sn is always a bounded. Sn is always a bounded. Not every lattice, Arafat. Let's take lattice like R plus circle, R minimum maximum. Set of real number. Set of real number is unbounded. Even set of natural number. Set of natural number is unbounded. They are lattice, but they are not bounded lattice. Okay. You cannot figure out one elements and zero I elements and 0 elements for R natural number. Okay. Good. So moving forward. So complement elements. The next concept is the complement elements. So what is the task now? You have to figure out what is the complement elements of any lattice. So first of all, L star plus circle 0i. L star plus circle 0i. Whenever 0 and I is given to you, that means it's a bounded lattice. So to start the complement elements, so to start the definition of complement elements, we need a bounded lattice. And I just told you what is a bounded lattice. So L star plus circle 0i is going to be a bounded lattice. Then two elements A and B of capital L, any two elements A and B from capital L are called complement of each other. A and B are called complement of each other if A star B is equals to 0 element and at the same time A plus circle B equals to I elements. Alright, both simultaneously satisfying. Hence, I can say that A is a complement of B. The notation of complement is A prime. A prime equals to B. I can say A prime equals to B or B prime equals to A. When I can say if A star B equals to that 0 element and A plus circle B is equals to I element. So you know what's the meaning of plus circle and star. Star means GLB, plus circle means LUB. Okay, it depends on the relation what is a star and plus circle. So always you have to check this one. If both simultaneous, not only is not single property, you have to check these two both simultaneously. Okay, if one satisfying another not satisfying, then the complement does not exist. One satisfying the another not satisfying means complement does not exist. To have the complement, we must have to satisfy these two properties simultaneously. All right, so let's take a look at that examples. So before starting example, what we need to know, complemented lattice. So what is a complemented lattice? A bounded lattice L star plus circle 0i is called a complemented lattice. It's called a complemented lattice if each elements of L, each elements of the set has complement in L, inside L. Again, whenever we have any bounded lattice, the first condition, it must be a bounded lattice. So to have bounded lattice, we must need the 0 element I elements. Okay, so 0 elements I element present means bounded lattice. Bounded lattice means with one extra condition. Extra condition is each and every elements of L, each and every elements of L is having its own complement, and all these complements are belonging to capital L. Clear? So that much you have to check. If it is simultaneously satisfying, then we can say that L star plus circle 0 I is a complemented lattice. So since it's a complemented lattice, so we have to change the notation. We are going to change the notation like this: L star plus circle 0 I was there, with that another extra operation, that is prime. This prime denotes that this is complemented lattice. So one lattice is, you can say this is complemented lattice if the bounded lattice plus each and every elements of that set is going to be is having its own complement. Okay, so now we'll go for the example. The first example, check whether S24 GCD LCM is a complemented lattice or not. Okay, so S24 GCD LCM. So first you need to know what is S24. We all know what is S24. 1 2 3 4 6 8 12 24. So S24 is 1 2 3 4 6 8 12 24. 8 elements are there in S24. Now what is the GLB of S24? GLB of S24 is nothing but your zero elements. All right, so to calculate the zero elements, you have to calculate the GLB. So GLB of S24 is your zero element, and zero elements is your 1. And similarly, what is your I elements? I elements means LCM. LCM of S24 is 24. So I elements and zero element present means it's a bounded lattice. So bounded lattice means we can proceed for checking complemented lattice. But is it a complemented lattice? Is each and every element is having their complements exist inside S24? Let's check. No, it's not a complemented lattice, because 2 is an element whose complement does not exist. You may ask me, so why? Because there is no such element inside S24 such that I can write 2 star B equals to 0 element, that is 1, 2 star B equals to 1, and 2 plus circle B equals to I elements, that means 24. Any element present inside this, let's take, this is 2, I am checking for 2, let's take 3. So what is the GLB of 2 and 3? GLB means GCD. GLB means GCD. So GCD of 2 and 3 is 1. Okay, I'm satisfied. But simultaneously you have to check LCM of 2 and 3. Is LCM of 2 and 3 is 24? No. LCM of 2 and 3 is 6. Alright, so GLB of 2 and 3 is 1, that is good. I'm satisfied with 0 element. But LCM of 2 and 3 is 6, which is not equals to 24. Similarly, 2 and 4. Check 2 and 4. Not possible. 2 and 6. Not possible. 2 and 8. Not possible. 2 and 12. Not possible. 2 and 24. Also not possible. And 2 and 1 is also not possible. So you cannot figure out any single complement from 2. Okay. So 2 is having no complement. Now you may ask me, sir, is there any element present inside S24 which is having complements? Yes, there is an element. There is a 2 elements whose complement present inside S24. Now it is your task to figure out what are those elements whose complement present inside S24 and what are they. You have to write down on chat box that particular elements whose complement present inside S24. Write down that elements inside chat box and also write down their complement. How many elements present inside S24 whose complement presence? Matthews, write 6, 8, 8, 12. Sorry Matthews, this is wrong. If I take 6 and 8, 6 and 8 are not complement to each other. 6 complement is 8 you are talking about. So 6 complement is 8 means GCD of 6, 8 should be 1. Is it 1? Is it 1? No. Because 1 is your 0 element. GCD of 6 and 8 is not equals to 1. So we'll stop there. 6 is not 6 complement is not 8. Matthew says 3. 3 and 8 is okay. So 3 and 8. GCD of 3 and 8 is 1. LCM of 3 and 8 is 24. So that means this is 0 element and this is I elements. That means satisfying. So 3 and 8 are complement of each other. So 3 complement is 8. 8 complement is 3. Is there any other complement elements exist? Any other complement pair exist inside S24? Try to figure out any other complement figure. Another complement figure exists inside S24. Matthews, all of you try to figure out another complement figure. Our complement pair is exist. figured out? All right, so yes, 124 is the correct answer, Matthews and Arafat. So 1 is complement of 24, 24 is a complement of 1. So always 0 element is a complement of I elements, I elements is a complement of 0 elements. So by default it's true. So in this case we get two complements, but not each and every pair of elements are complement of each other. That's why this is not a complemented lattice. You may ask me that though we can figure out one elements like 3 and 8, they are a pair of complement elements, but still not every elements are having complements. That's why S24 is not a complemented lattice. Okay, so moving forwards for the next example, go for it. Check whether it is a complemented lattice or not. Write down your answer on chat box quick. A equals to ABCD. 4 elements is there. ABCD. Okay, think about this. Don't need to show it is lattice. It is lattice. I don't need to. You don't need to show it is lattice. Just check only the boundedness and complemented lattice or not. Okay. All right, got responses. Yes, Hamna. 0 elements is phi, I elements is A. Perfect. 0 elements and I equals to phi and I elements is A. Now you have to check whether it's a complemented lattice or not. Matthew says not complemented. A union B equals to AB, but I is ABCD. Okay. But Matthews, you have to figure out that whether each and every element is having its own complement or not. It is correct that B is not a complement of A, but there may be possible some other elements which is complement of A. Okay, some other set exists which is a complement of A. Now it is true that A union B is not equals to is equals to AB. Okay, that means B is not a complement of A. That's good, but it may be possible some other set like AB, BC, whatever, BCD, ACD. It may be the complement of A. Okay, try to figure out.